simple harmonic motion. I want to analyze this motion from a perspective of dynamics, of energy, of momentum, and kinematics briefly. We look at the mass on a spring. The spring is normally much shorter. I put the mass on it under the force of gravity. It extends to a new equilibrium position. So we say dynamics. We know the vector sum of the forces must be equal to mass times acceleration. At this point, we're in equilibrium, the acceleration is zero. So what does that mean? It means the force of gravity pulling down and the tension in the spring must be equal and opposite. And so sure, the tension in the string is k times x. What's x? X is that change in length from its relaxed position to the extended position. But I can refer to this as the new equilibrium position and say here the new x is defined as being 0. And so here they're in equilibrium. The force of gravity downward and the extended spring pulling upward are equal and opposite. If I pull down further, there's an extra force, kx, pulling up. If I push upward, the spring pulls with kx less than before, so there's a net force kx pushing downward. And so if this is defined as 0, that means if I'm up here, there's a net force kx downward, and if I'm here, there's a net force kx upward. So this is a stable equilibrium point because when I push away from equilibrium, there's a restoring force to pull it back. And this is what we would call negative physical feedback. And so what we can see is gravity here actually doesn't affect the behavior. This would be the same if there was no gravity. For instance, if we laid this level and the object was allowed to oscillate back and forth, and then it would only be spring driven. Using these near frictionless carts on a track, we can show how gravity doesn't matter. They still oscillate back and forth. Adding gravity back to the picture only changes the equilibrium point, shifts the equilibrium point about which they oscillate, but doesn't change their oscillation frequency. However, mass changes the oscillation frequency quite a bit. By increasing the mass, we lower the acceleration, and therefore the frequency drops. From a perspective of energy, we have an exchange of potential energy in the spring and kinetic energy in the mass back and forth. We can define an equilibrium position at x equals 0. And we can oscillate about this point at some amplitude, capital X, which is what your book uses. Other books use amplitude A, but we'll use amplitude X like your book. And so let's say it's extending above and below some amplitude, capital X. We look at energy, we remember our work energy theorem, and that's that work is equal to the change in energy. And so are we doing any external work on the system? There's no fuel going in to speed it up. It's true there's a little bit of friction that will ultimately bring this to rest if we wait long enough. But let's go with a frictionless system. And so there's no work being done, so the change in energy will be 0. And so we know that the total energy, which is the kinetic energy, plus the potential energy, must be equal to a constant. And so the kinetic energy is 1/2 mv squared, and the potential energy in the spring is 1/2 kx squared, where x is how far it is from the equilibrium. As it oscillates back and forth, at its turning point right here, what is the velocity? We recognize as it's turning around, the velocity is 0, and so the kinetic energy is 0, and all the energy, the entire energy, is in the potential energy of the spring. And so this is where we have 1/2 kx amplitude squared is equal to the total energy. When it passes through x equals 0, that's the equilibrium point. That's when x equals 0 and there's no potential energy. So therefore, all the energy must be in the kinetic energy, 1/2 mv squared. So this is 1/2 mv squared max is equal to the total energy. And so this sum of energy, the kinetic energy plus the potential energy, is equal to the total energy, is equal to 1/2 kx squared max, which is the amplitude, is equal to the maximum kinetic energy, 1/2 mv max squared, which is at x equals 0. And so as it bounces up and down from all the energy being in the potential energy to all the energy being in the kinetic energy, somewhere in between, it's going to have some potential energy and some kinetic energy. And the total of the two is going to equal the sum of the energies, which is the same as the maximum potential energy, which is the same as the maximum kinetic energy, because the energy must remain constant in the system over time. How about momentum? As this bounces up and down, is momentum conserved? And you say, well, we know momentum is conserved, of course, but look at the mass. We know in the middle, it's moving downward very fast or upward very fast. And at the top, it's not moving at all. So its momentum is changing. We say, okay, what causes a change of momentum? We remember an external force is equal to the rate of change of momentum. And so there's an external force acting on this. The Earth is pulling it up or pushing it down, depending on whether or not it's above the equilibrium point or below the equilibrium point. So it would make sense that as this is bouncing down and up, the Earth would be bouncing up and down. So let's take a look at a coupled oscillator, two masses attached to the same string. If we see that the two masses are the same, they will oscillate with equal amplitude and equal velocities about the center point of the spring. However, if one mass is larger than the other, the two masses will oscillate about a point that is not the center of mass, but closer to the larger mass. And the larger mass will oscillate with a smaller amplitude and a smaller velocity. And we can make it extreme if we make the mass very large, it barely moves at all. So if we recognize that this mass is bouncing up and down, but it's connected to the Earth that is bouncing oppositely, we could say at some point this is headed downward at some speed v0, and the Earth is headed upward at the same speed? No, because it's the momenta that have to be equal and opposite. And so what we should say is this is some momentum downward, and the Earth has some momentum upward, and they're equal and opposite. And so we know that the mass of the Earth is much larger, so its velocity is going to be much smaller than this one, and it will barely move. How about the energy? Do these guys share energy equally then? Is half of the energy in the oscillator actually in the Earth moving up and down? We think kinetic energy is equal to 1/2 mv squared. But I'll choose to express it as p squared over 2m. Why do I do that? Because the momentum of both of these are equal and opposite. So they have the same numerator. But the denominator, the mass, the Earth's mass is huge. So in fact, the Earth's kinetic energy is negligible because its mass is so much larger than the mass of the oscillator. And it is reasonable for us to say that the oscillator itself holds all the kinetic energy in the system. So let's take a look at kinematics. We can see that this mass bouncing up and down behaves identical to a mass on a wheel as the wheel rotates in a circle and the mass is viewed from the side. So you can see as this mass oscillates up and down, its behavior is the same as a ping pong ball attached to the vinyl record, rotating at the same frequency that the mass is bouncing up and down. So can we define the motion of this oscillator using this knowledge? And so let's take a look. If we are oscillating at this amplitude At some point, let's say the mass is right here, and let's say this is moving in this direction at some speed, omega naught. And so this is going around, but we just see it going up and down because we're looking at it from the side. And so, okay, let's take a look. We have some angle theta here. And what do we see? That height is equal to the radius times the cosine of theta. And so x is equal to radius times cosine of theta. But instead of radius, we're going to call this the amplitude, right? Because when this is all the way up, the amplitude of the oscillation is the same as the radius of the circle. Remember our displacement equation? X is equal to x naught plus v naught t plus 1/2 at squared. Well, we have that for theta as well. Theta at any given time is equal to theta naught plus omega naught t plus 1/2 alpha t squared. And so we're talking about constant rotational motion and constant oscillation. There's no rotational acceleration. And this is what theta is. And so now I can write x as a function of time is equal to some amplitude times cosine of omega naught t plus theta naught. So how would we graph height over time as this thing bounced up and down? Well, we know how cosine varies with theta. It's sinusoidally varying about 0. And so cosine x of theta would go from positive x to negative x, and this is that capital X amplitude. And it would go like this. And we know the measurement for a full oscillation is going to be 2 pi. And so if we wanted to show this oscillation in time, rather than make this verse theta, we make this verse omega naught t plus theta naught. Okay, and for simplicity again, let's leave theta naught out of this. And so we could see that the measurement to come back to where you are, that would be one complete cycle, or one period, t, is defined by omega naught times that one period is equal to 2 pi. Or omega naught is equal to 2 pi over the period. Okay, 1 over the period is a frequency, and so omega naught is equal to 2 pi times the frequency. Another way to look at this would be to say, how much time does it take to come back to where you are? Well, we know that would be 1 period, and that's going to be equal to 2 pi divided by omega naught. So that's the amount of time to go up and down. And then we could make the step of let's change this to a displacement versus time graph. And what would the time be for 2 pi for one oscillation? It would be 1 period, which is 2 pi divided by omega naught. And so what does theta do? What theta does is it shifts this. For instance, if instead of being up here at t equals 0, it was actually right here on its way down. That means it would have been at this point headed downward, which means theta would have been pi by 2. And so what would that do? If we had theta is pi by 2, it would have shifted the curve to here. And so what happens as you increase this value, the curve shifts to the left. And so what we see in time, this oscillates up and down. It's moving very fast through these 2 points, but slows down and actually comes to a rest for a moment at the turning points.